So thank you so much. Thank you so much to be there at this early time. I really appreciate, and it's really a pleasure for me to be here today at TIDES to present you our innovative technology. And we are especially glad to be here with my team also, because it's our first time that we present data with collaboration on using our technology to drive peptides and oligonucleotides. So today I will talk about drying. Audrey Amadou, I'm process engineer. Yes, it's sometimes a little bit another word, but I will be careful. I will try to do samples that I can. And please be fair also, I'm not chemical at all, so sometimes it could be interesting, we can say. Few words about our company. My company is an American company. We are based in Chicago. We are a division of spraying system, and we are solid dosage equipment manufacturer for more than 40 years. And yes, the last 10 years, we developed a new drying technology, namely electrostatic drying. We don't do only electrostatic drying. We have fluidized bed, ice granulation, milling, and we do by ourselves our process automatization to give us the maximum flexibility that we can when we have a request from the customer. But today I will focus on our last baby, that is an electrostatic drying. To support this new and innovative technology, we made the choice to have laboratory all around the world. So with some different size of equipment, and also to do a proof of concept for our customer, and also to develop our own research. So we have a laboratory in Melbourne in Australia, in Shanghai in China, and for Europe, we are based in France. And for US, we are based in Chicago, where we have also our main manufacturing plants. So it's where we welcome our customer and also all people where we have some collaboration together. I say yes. When we arrive with this new technology, we need to do some proof of concept, especially because we tried new compounds that are coming in the market, and we need to understand well what is challenging and how technology can help. So for that, we developed now more than 7 years some different collaboration around the Europe and also in US and Austria and China too. But specifically in Europe, we have a collaboration with Bologna University for peptides, with CPI, and thank you. I saw that there you are here too. Thank you for supporting us for oligonucleotides. And we also work on enzyme with Leuven University, and on the drug inhalation, I could be also interesting with RCP in Austria. So I talk a lot about, we can say, starting application drying, but what is this technology? What is electrostatic drying? So electrostatic drying that we mentioned is like an alternative to the lyophilization. The idea is to work continuously. That means that we have a feedstock solution that we spray at the top of the tower. Thanks to an electrostatic nozzle, we create we create droplets that is dry in the drying chamber, and we obtain at the end powder. That means that after a few seconds that you spray, you obtain powder. Talking about the drying gas, we made the choice to have nitrogen, and the temperature of the nitrogen is between 60 to 140, but I will show you after the temperature of the products that we have. We try to be below 60 degrees C. That means it's a really gentle drying for ones that they know more spray dry. So we are really working really at lower temperature. To little bit compare with lyophilization. So that I say we work continuously, that means that we obtain the product, that means that we can also analyze the product close online. And also, we work a lot to improve our technology to avoid to have the concentration step. That is the third step. We are able to work, for example, with a concentration of 10 grams per liter. After that, when you obtain your powder, you don't need to mill it. That sometimes happens when you have your cake. And in our case, you obtain directly the particle size that you want. Most of the time, we are between 3 microns. That's why we talk about inhalation to 20, 15 micron. And after that, we can optimize around that. So when the powder that you obtain, we can say good density, but higher density than lyophilization. And I will show you some video after that. We have also a good flowability of our powder. Two last points. The first one is when we develop a new application with our technology, this application is peptide and oligonucleotides in this case, we try to be sure that when we do the presentation and we arrive to the market, that we obtain the same quality than the freeze dryer of better, that it's the best too. So last point is the fact that we did some work to show also that we are able to reduce time, of course, because freeze dry it's most of time 2, 3, 4 days. And in our case, after a few minutes, you can analyze your powder and also reduce our energy consumption, especially talking about electricity. Okay, this is the more scientific slide. I promise I will be really fast. It's just to give you an idea that the electrostatic charge, it's really work at different stage during the drying. We identify that we think the main one, and we have some experiments showing that too. So the interesting things is starting in the nozzle. So you have the nozzle, you create, we can see your primary droplets that you have after, thanks to your spray, to divide in smaller droplets. But you need to have to be able to detach your droplet. And thanks to the electrostatic charge, you reduce your surface tension. That means that when you have a really high viscous solution, I have in mind more hyaluronic acid, for example, you are able to detach your droplet to create after that fine droplet and dry them. After that, so you create multiple smaller droplets that you charge with the same positive or negative charge. That means that you have repulsion between them. And in this case, you are able to have more space around the droplet to dry them and give you drying more efficiently. At the end, and this is the most difficult phenomena, I think, to explain, but I will really fast. The idea is you charge also your droplets at the surface and a little bit inside, and you can create an orientation of your solvent. Most of the time, we work with water, and you can have a good, better diffusivity of your molecule of water thanks to the electrostatic charge and your orientation of your molecules. That offer us the possibility to work at lower temperature and gentle temperature. I just put this slide, be sure that it's not a commercial presentation, but it's just to show you that we want to have a scalable technology. That means that when we arrive to the market, we wanted also to be able to offer the different size, laboratory size with the model 0.1 and model 1, and to go in up to the industrial scale. All the numbers that you see, it's a maximum evaporation per hour of water at maximum condition, maximum temperature. And I just want to show you that we also develop our technology to be solvent duty. That means that you can use organic solvent in our system, especially if you work with acetonitrile and acid acetic. This is a little bit like kind of resume about our technology. So we use nitrogen like a drying gas. That means that we avoid to have any oxidation to have no oxidation, sorry. We are able, that I show you, to work at lower temperatures that for conventional spray dryer, for someone that are familiar more with spray dry. We have a good preservation of IP, and something that I not really mentioned before, it's we have also an homogeneous product. The fact to work continuously help us to have this homogeneous product and with the particle size that you want. It's a continuous process that I say. I not really mentioned, but after that, we can discuss. We are able to recycling the solvent. I show you we have different scale, and we know exactly how to do the scale up between the lab scale to the industrial scale. And we use less energy than lyophilization. So I think this is the main interesting part for everyone. And so the case of study, so we have two case of study, more proof of concept, we can say, on peptides and oligonucleotides, thanks to the different collaborations that we have. So I will start with this collaboration with Bologna University. We work with Professor Tolomili and Professor Cabri. We have a PhD student together. We arrive still at the end, we can say. So when we start this project, we can say, two main goals. The first one, it was to able to spray low solid content solution between 40 to 150 grams per liter with and without organic solvent. I think the main point, it was to be sure that we have the absence of impurity in peptide when we dry them. So this is an example of peptide, the if I'm good, where you can see that you have different chemical sites with different reactions that it can happen to create impurity. The idea of this team was to isolate one by one the different reactions that we can have, to have 7, and this only 6, and I will show you the 7 one after that, to create like a kind of library of peptides that we have to try. So our PhD student synthesized by himself all the peptides that you can see here, and also double check the impurities that we can have. She developed all the chromatograph analytic to double check if everything is good after trying. Our first work was focused on racemization. So for this one, we wanted to a little bit more in detail, we can say. So we do an experimental design. I'm process engineer, so I like experimental design. So we make the choice to fix the inlet temperature, but change the voltage. So the voltage, it's the electrostatic charge that we apply in our tower. And we change also the concentration between 40 to 120. And we have also changing the drying gas. The drying gas is give you the capability of evaporation in your tower, and also manage the residence time. Faster, it's your drying gas flow. Lower, it's your residence time. For this work, we to solubilize peptide, we use water, and we use also acetic acid at 6%. The great news when we check the chromatography analysis is that we have no racemization of histidine. So this was a really great news for us. And talking about the moisture content, we are value between 4 to 9.1. I was not so happy, to be honest, with the 1.1. But when we're checking and analyze our experimental design, we were able to see that the main factor is the drying gas flow, and to have a good moisture content that I prefer to be below 5. You need to decrease your drying gas flow. That means that you increase your residence time in your tower. So after that, we're checking the other sequencing. So for that, we use different contrarian, we use different solvents, with different concentration. We fix the concentration of peptides at 18 grams per liter. And I know because my PhD student coming and say, oh, I want to go lower that we can. So she put an inlet temperature at 65 degrees C. And we apply a voltage at 4, and also we fix the drying gas flow at 5 kilovolts and 4 for the drying gas flow. So the main result, I try to synthesize all in this table. So the great news is that we obtain powder for all peptides. The moisture content was so quite good. Again, I say I prefer to be below 5. So, but we show that thanks to an experimental design, as that means an optimization of the operating condition, we can reach this value. We have no impurity creation for no one. And we know the importance also to check the solvent residue of acetonitrile and acid acetic. So this it's still in progress, but to be sure that we are ready and we can do the scale up, we work before as a team in US working on it to be sure that with our technology we are allowed to have a low solvent residue, especially for acetonitrile when we talk about legislation. So for that, the team in US work with the biggest model, the model that we have at industrial scale. They work with BSA. It's very difficult to have a large quantity of peptides, so we made the choice to work with BSA. You can see we talk about 20 kilogram per hour. And they do a mixing between acetonitrile and water 50-50. We wanted to be at the worst case, talking about concentration. So we work at 10 grams per liter. That is, we can say, really, really low. We can be a little bit below, but not so much. The great news, it's talking about acetonitrile residue. We are below the legislation. So our equipment, it's ready. And we wanted also to double check that you see the process here, that is the powder recovery. We conduct a first one with few hours, but we consider that our technology can work for days. So if we talk about few hours, we are around 92% of powder recovery. But the interesting thing is to mimic, we can say that we can happen if we run days. And in this case, we can say we are higher than 98% in this case. You can see the inlet temperature, we are between 80 and 90 and 95, but the outlet temperature, that means the powder temperature, the product temperature, we are really below 50%, 50 degrees C. That is, says that it's really gentle drying. So to conclude, we check that we have an absence of property for all the 6 chemical sites. We still are working on the diffuser bridge reaction. The trial was done 2 weeks ago, and we just received the last week some data to say that we have no impurity creation. So we are really happy, and we're still waiting the solvent residue content, but we are still comfortable when we see the results that we have with BSA. The inlet temperature that you can see, it's really low. We can say for spray dry between 65 degrees C to 120, and the product temperature is below 60 degrees C, even if 50 degrees C. I wanted to show also the importance to optimize the operating condition. This is for, I think, all process, you need to do that. An experimental design, it's a great way to do it, and especially in our case, to reduce the moisture content. We show that we are able to have, let's say, an equipment, industrial equipment ready with a good acetonitrile residue, with a good powder recovery also. So the next one, it's an application with oligonucleotides. It's a collaboration with CPI, with Barry Kazé, Fiona McDonald, and Claire MacLeod. Sorry for the spelling. The main goal, we just conduct 6 runs. The main goal was to check the feasibility to use electrostatic drying instead of lyophilization to dry oligonucleotides. We use a new oligonucleotides model that it was synthesized and purified at CP high. The solvent it's water, and that you can see step by step we reduce the concentration, and we are at 10 grams per liter. For this work, we use our small bench model, that is the model zero point 0.1, and we check the powder shape, we can say, with a SEM picture, and also we analyze with chromatography if we have some, the quality of the oligonucleotide after drying. So for each trans, we obtain powder that you can see. The particle size of the powder is between 2 to 5 microns. We focus on the run 1 and the run 6 with a net temperature at 75 degrees to 90 degrees C. That you can see the product temperature, it's below 40 degrees C. And when you're checking the purity, we have close to the same purity before and after drying. So we are really proud of that. Okay. So we also double check a little bit like a comparison on that you usually obtain with lyophilization. So some video was done at CP high to show how it's flowability of the powder. That means that's really easy, you can see. And also how it's easily to handle the powder that we obtain to fill it after. And also they did some tests about reconstitution in water, just a gentle drying like this, and they observed no gelling that they can observe in other cases. So to conclude, Sam, it's really encouraging result. It was successful. The oligonucleotide was successfully tried with our technology. We show that it was possible to dry oligos with electrostatic drying. We have the comparable purity between before and after drying, and that you can see we have a good handling and good flowability of our powder. The next step is to do a little bit. It's to do the scale up. That it was, to be fair, done in the past with another project, so we are really comfortable to do it. And that's true. That is missing is to a fair comparison with lyophilization to really compare a powder together. That it will be done. So to conclude, so that I say you, we are happy to present you for the first time the data with peptides and oligonucleotides, so that you can see for both we have an absence of impurity. We have a good handling, good flowability of the powder. We don't need to mill it after that. And we can say for both, we check how it's a scale up, and we show that we have a good scale up between the model 0.1 to the model 4 and the model 32. So we can say our technology is ready to work in industrial scale. To finish, I would like to say a big thanks to Bologna University team, CPI team, Fluidair team in Europe and in US. And you are more than welcome in our booth. That is the number 114. Thank you so much for your attention. Thank you so much to be here at this really early time. Thank you.
Thank you very much for your introduction. Just have a simple question. Is the function of this electrostatic is to break down the droplet? Do you still need a nozzle in that machine?
Oh no, to break down the droplet, it's more the atomizing gas. We use a bifluid nozzle, so it's more the atomizing gas that we put around the liquid that it will lose its function. No, really the function of the electrostatic charge, it's more to have to repulse the droplet between, to give more space for the drying gas, and also more, we can say, chemical kinetic for the diffusion inside the droplets.
Okay, yeah, I see. Thank you.
You're welcome. And something that I forget to say, if you want that we send to you directly the presentation, you can put your card in this table and we will do it.
Any further questions for our speaker? Then I'll have another round of applause, please.
Thank you.
Thank you very much, Audrey.